Hello everyone, and welcome back. Last time we started to look at the conservation of linear momentum, and we're going to continue with that today. One thing we noticed was, last time we started to look at more complicated systems. Rather than single particles moving around, we started to look at numbers of particles and how they interacted with each other. One thing we noticed was that when we defined this quantity called the momentum, the linear momentum specifically, which is the mass times the velocity vector, which gives us the momentum vector, so momentum is a vector quantity. One thing we noticed was that when we had a system of objects, we could divide the forces acting on the system into two parts. There were the external forces and the internal forces. The external forces were forces that were exerted onto the system from something outside, externally to the system. The internal forces were the forces that the particles exerted on each other, which always came in pairs, according to Newton's third law. And so when we looked at the way the forces affected the motion of the system, the internal forces would cancel out when we looked at the system in its entirety. In particular, when we looked at the total momentum of the system. When we sum up the momenta of each individual particle, the total momentum of the system was only affected by external forces, not the internal forces. What we're going to do today is look at a very particular type of system and how it interacts by way of collisions, a collision. So we're going to assume, to start out with, that we only have two objects, two particles, that are going to interact with each other by way of some kind of collision. So we're going to assume that whatever interaction they have, it takes place over a short amount of time. The interacting forces, the internal forces then of the system, we will assume dominate the change in the motion, or change in the motions, so that we're going to assume there either are no external forces, or the external forces can be neglected or ignored actually during the collision. So for the collision, we're going to look at two different situations. We'll have the situation initially that is the motion of the particles before they collide, and then we'll look at the motion of the particles after they collide. We're going to look at this very generally. So this would apply for objects that are coming together like this, for one object chasing the other or chasing the other way, or one is stationary and is hit by the second one. Doesn't matter. We're going to assume general forms for the velocities, both initially and finally, but then if we wanted to change the direction of either one, we would just give that particle a negative velocity. Okay, so let's take a look and see what we get. Let's imagine that we start out with, over here, I'll draw the initial situation. Let's imagine we've got two masses, m1 and m2, and we'll give them some initial velocities. So we'll say that m1 is moving at some velocity v1, and we'll call that v1 initial for its velocity before the collision. m2, we will assume, has some velocity v2 initial. Again, we're going to say that both of these are positive, but if, say, m2 was going this way, then v2 initial would be a negative number. These are the components of the velocities in the one dimension that we're considering. We'll assume a one-dimensional collision for the moment. So here's our initial situation. And then after the collision, we have the final situation. And it's going to look a lot like the initial situation. We'll have m1 and m2. But now, rather than v1 initial and v2 initial, we will assume that the velocities are v1 final and v2 final. Okay. Whatever the internal forces, we know that the total momentum is going to be conserved. So we can write down the conservation of momentum result to start with. So what do we have? We've got the total initial momentum is going to be the momentum of object 1 plus the momentum of object 2. So we'll have m1 v1 initial plus m2 v2 initial. That's got to be equal to the total final momentum, which is the final momentum of object 1 plus the final momentum of object 2. So this will be m1 v1 final plus M2 V2 final. Okay, very good. Now I want to rearrange these just a little bit. I want to take the mass 2 quantities and put them on one side, and the mass 1 quantities and put them on the other side. So let's take the mass 1, M1 V1 final, and let's bring that over here. And what will we have? We can factor out M1, and we'll have M1 times V1 initial minus V1 final. And that must equal, bringing the M2 term over here, factoring out M2, we'll have this equals M2 times V2 final minus V2 initial. Okay? Very, very good. Notice we've got V1 initial minus V1 final, but over here we've got V2 final minus V2 initial. Okay? So we'll take a look at this more shortly. At this point, we can't necessarily solve for unknowns unless we know something more about the interaction. The internal forces can have an effect on these velocities. As long as the momentum is conserved, the internal forces can still change the values of the final velocities. There are different kinds of collisions depending on what those internal forces are. If the internal forces are conservative forces, then kinetic energy will be conserved and the total initial kinetic energy will equal the total final kinetic energy. If those internal forces are not conservative, then kinetic energy can be lost. Some of it can be lost, and we'll see exactly how much could be lost. And in that case, the initial kinetic energy will not equal the final kinetic energy. Let's start to begin with by looking at a situation where the internal forces are conservative, so that kinetic energy is conserved. That type of interaction is called an elastic collision. An elastic collision means that kinetic energy is conserved. So let's start now with the assumption that the kinetic energy is conserved, which means the initial kinetic energy must equal the final kinetic energy. So what does that mean? Well, the initial kinetic energy will be the sum of the kinetic energies of the first masses. So we've got 1/2 m1 v1 initial squared. That's the kinetic energy of the first mass initially, plus 1/2 m2 v2 initial squared. So that's the kinetic energy of the second mass initially. That is the total initial kinetic energy. This must equal the total final kinetic energy, which will be the sum of the kinetic energies of each mass finally. So 1/2 m1 v1 final squared plus 1/2 m1 v2 final squared. Okay? Very good. Now, what we're going to do is, again, we're going to put the m1 terms on one side, the m2 terms on the other side. So we'll have, let's factor out the 1/2 as well. So we'll multiply the whole thing by 2. That gets rid of the 1/2 terms. Let's bring the v1 final term over here. So we have m1 times v1 initial squared minus v1 final squared. And that is going to equal m2, whoops, sorry, this should be, that I wrote m1, but that should be m2. That's going to be m2 times v2 final squared minus, here, v2 initial squared. Okay, there we go. And again, notice we've got initial minus final on one side and final minus initial on the other side. Okay. Notice what do we have here? We've got the difference of two squares, like a squared minus b squared. And we know that we can factor a squared minus b squared into a plus b times a minus b. So let's factor both of these sides out. And what do we get? We get m1 times, we'll do the difference first. So v1 initial minus v1 final times v1 initial plus v1 final. Okay, so A minus B times A plus B. This equals M2 times, we're going to do the same thing over here, V2 final minus V1 to V2 initial times V2 final plus V2 initial. Okay, there we go. Now, notice, what do we have here? The first term here, M1 V1 initial minus V1 final. Oh, but it's exactly what we have here. M1 V1 initial minus V1 final. And the first term over here, M2 V2 final minus V2 initial, is exactly the term we have up here. M2 V2 final minus V2 initial. So we know that this term equals this term, which means we could divide them off if, under one condition, they're not 0. If these are both 0, then we can't divide off 0 from both sides. So let's assume that these are not equal to 0. So what does that mean? When would these be 0? Well, both of these would be 0 if V1 initial was equal to V1 final and V2 final was equal to V2 initial. In other words, V2 initial was equal to V2 final. Well, what would that mean? When would that be the case? When would V1 initial equal V1 final and V2 initial equal V2 final? Well, that would be the case if the two objects never interacted with each other. So if we had a situation where the two objects were coming together and missed each other and had no interaction, then V1 initial would equal V1 final and V2 initial would equal to V2 final. So that's basically just the situation where nothing happens, where the two objects miss each other. So let's assume that does not happen. Let's imagine they actually hit. So we'll assume they actually hit, in which case this will not equal that, and this will not equal that, and that will not equal 0. Great. So we can assume then that this equals this and does not equal 0, so we can factor out both from each side. We can factor off this one from this side and this one from that side because they're equal to each other. And what does that leave us? It will leave us with this term equals this term. In other words, V1 initial plus V1 final must equal V2 final plus V2 initial. Now, rather than getting the 1s on one side and the 2s on the other, I want to get the initials on one side and the finals on the other. So let's bring V2 final over here. So, or let's bring these over here actually. So V2 final minus V1 final, V2 final minus V1 final. So that's bringing that over there. Let's bring this over here. Will equal V1 initial minus V2 initial. Or, I'm going to pull out a negative sign, negative V2 initial minus V1 initial. Okay? Let me rewrite that where we can see it a little bit easier. I'm going to bring this last equation up here. V2 final minus V1 final equals negative V2 initial minus V1 initial. So this is an interesting result. Notice we've got V2 minus V1, and we've got it finally, and V2 minus V1, we've got it initially. And they are equal with a minus sign. So whatever this quantity is, V2 minus V1, it changes sign from before the collision to after the collision. The value of it after the collision is the negative of the value of it before the collision. What is this? V2 minus V1. That's called the relative velocity. I'll put it in a different color here. V2 minus V1 is called VREL, the relative velocity. When we stick some numbers in here, we'll calculate that and we'll see more physically what this means. And what this is telling us then is that VREL finally is equal to negative VREL initially. The relative velocity basically tells us how rapidly the two objects are coming together or moving apart. Are they coming together fast? Are they moving apart fast? Or are they coming together slowly? They could come together slowly by both objects coming together like this. They could come together slowly if one was chasing the other one and kind of came up behind it slowly, or anything like that. It's basically telling us how rapidly are they coming together and then going apart. And what it's telling us is that they come together at the same speed as they move apart after the collision. One is positive, one is negative. Let's look at this. V2 minus V1. V2 minus V1, V2 minus V1. Let's just imagine, just for the sake of argument, that this were larger than that. V2 was larger than V1. Then V2 minus V1 would be a positive number. So VREL is positive if they are moving apart. VREL is negative if they're coming together. So if V1 were larger than V2 so that they could actually catch up, this would be a negative quantity. If V2 were larger than V1, this would be positive, and they would be moving apart. So coming together, they have a negative relative velocity. Moving apart, they have a positive relative velocity. Okay, very, very good. Let's take a look at some numbers. Let's stick some numbers in here and see what happens.